So I have absolutely nothing new to say. I mean, I do, but I'm not going to be saying it today. So when I agreed to come to this conference a long time ago, it was because I was interested in coming. And then, will you speak? Well, sure, one can always, I can always talk. I mean, that's not a problem. But then I realized the only thing I've done in recent years connected with multiple zeta values, which most people in mind is this thing about zeta 222, 3222. But the people are interested, have seen it, many things have already been done during this conference with it, and I certainly didn't want to repeat that story. And so I thought maybe I'd go back. So think of this as the lecture that should have preceded the conference. I want to give some background things about bits and pieces of mathematics, mostly number theory, which are extremely familiar. Each of them is very familiar to a lot of people, but probably each of them is not familiar to at least some people in this audience, especially physicists, but also mathematicians, and just sort of various nice things. So it's mostly very well-known things. Some of it's work of mine, but old. A couple of things are newer, if I get around to them. But this is mine, and it can be moved. So I don't need a seat. That's at least one problem I can solve. Okay, so the title had three ingredients: modular forms, differential equations, and I've forgotten the third. And then I'd written a resume which was so stupid that Pierre van Hoves cleverly didn't even publish it. He just left it out, which said, I will talk about these three topics and their connections with other things. It was slightly more detailed. So I want to, we've been hearing a lot about multiple zeta values. But at a certain time, there was a belief, even a conjecture, that maybe all of the periods coming from, for instance, Feynman integrals would somehow be in the world of multiple zetas. We now know very well that that's far from being the case, and therefore that the whole world of periods becomes of interest potentially in physics and is already of interest in mathematics. So in some sense, apart from multiple zetas, the most concrete things that fit the notion of periods are periods of classical modular forms, which is a very old subject, certainly one I've thought about for years, but again, not all physicists, I think, know it, not all mathematicians know it, and there are a couple of things to be said, although anything deep on that was also already said by Francis in his talk. And then there are also periods, well, let's say Picard-Fuchs differential equations, they've been mentioned in a couple of the talks here, that sometimes you have families of things, like families of elliptic curves, and then you also get periods, but now they're moving, satisfy differential equations. And this is one of the simplest examples comes from modular forms. So I'm going to be very, very elementary, certainly, well, not just at the beginning, the whole time. So first of all, let me remind modular forms. Certainly everyone knows what they are, but just to slightly fix notation, first I remind you about the slash operator. If gamma is an element of SL2, well, Z or even R, and K is some integer, then if I have a function from H, which is the upper half plane, Poincare plane in France, if I have a function f, then the slash operator sends f to s slash gamma, so it's a right operation, and it's the function of the upper half plane defined by this formula. So if gamma is either SL2Z or a subgroup, maybe a finite index, the only things are sometimes commensurable. With SL2Z, then one has mk of gamma, which is functions on the upper half plane, holomorphic, moderate growth, so polynomial somehow at infinity, moderate growth, and which are simply invariant in this fixed weight k. So k is the weight for all gamma in your chosen group. So it's convenient to write it that way rather than putting f of gamma tau equals c tau plus d to the k. So that's just for notation. And for some more notation, of course, if gamma is the full modular group, and just call it gamma 1, so SL2Z, then we have famous examples, of course, would include the Eisenstein series. So this would be a modular form of weight 4, or the function delta, which is q times the product 1 minus q to the n to the 24th. And sometimes I'll use eta, so eta is the 24th root of that. So this is a modular form, a cusp form of weight 12. And Q, oh, before I kill myself, I should move this out of the way. So, yeah, and Q, of course, is e to the 2 pi I z, e to the 2 pi I tau, rather. So, okay, that's just to have a couple of examples. And then the other thing, just for complete background, of course, everyone knows this, is just to remind you the connection between modular forms and elliptic curves. So if I have tau in the upper half plane, then I can make the corresponding elliptic curve, which is C modulo z tau plus z. And conversely, given any elliptic curve over C, so A and B are some complex numbers, then we know that we can write this using the Weierstrass P function or something as C modulo some lattice, where L is the set of is the space of values of the integral of the standard holomorphic form dx over y or dx over 2y or something over gamma in H1 of the curve. And then any lattice in C is generated by two numbers, omega 1 omega 2, so up to rescaling it's tau and 1. And of course, here you have the J invariant of the curve, which is 1728 times 4a cubed over 4a cubed plus 27b squared. And here you have J of tau, which is E4 cubed over delta. So this starts, again, I'm only writing down things that everyone knows so that everybody feels happy, at least for a while. And so you have this correspondence. So we have this sort of these 2 points of view. So that in particular means that later, if this elliptic curve varies, so this will become A of t and B of t, maybe two, for instance, rational functions of t, then J will also be a rational function of t. But J is also a modular function on SL2Z, and so with a little luck, T will be a modular function on some subgroup of SL2Z. And then the periods, which are these, so this thing is Z omega 1 plus Z omega 2. Locally, I can pick the basis, and if I move, then omega 1 and omega 2 move and satisfy a differential equation, which is the Picard-Fuchs equation. And of course, there's monodromy. If you come back, you've got a different basis, and so the monodromy lies in SL2Z. So we already have sort of connections built in between modular forms and differential equations and elliptic curves. So I now want to start with the classical periods. So let's think of delta. Well, I'm going to think of delta, and we're going to associate to it a polynomial, r delta of x. Again, this is very, very well known to number theorists, but maybe some people haven't seen how it works, and it doesn't take very long to go through it. So let me do it more generally. Let's assume that well, to keep things a little simpler. No, it doesn't matter. I was going to take a cusp form. I take any f, and what I want to use is a basic thing which is called Bohl's identity. So this is from, I don't know, 1940 or something, maybe it's earlier. And it says that if you have any function at all in the upper half plane or in C, and you map it to f slash gamma in a negative way, 2 minus k, k let's say is at least 2. And now if you take the k minus first derivative of that function, so remember this thing is a function of tau, and if you take the k minus first derivative of that, that's the same as if you take the k minus first derivative of f, and then you slash it now in weight k with gamma. So in other words, the k minus first derivative is an intertwining operator between two representations, the representation in weight 2 minus k and the representation in weight plus k. So now, therefore, if we have my function f in fk, I choose an f which maps under k minus 1-fold differentiation to f. Of course, I can always do that. So e.g., I'll call this simply f tilde. Well, usually I take out a 2 pi I, but let's not worry. So if I take delta tilde of tau, there'd be a 2 pi I somewhere, so up to 2 pi I to the 11th. This would be the sum, n from 1 to infinity, tau of n over n to the 11, q to the n, where the delta, I didn't say, I mean, delta, of course, I wrote the definition, but of course it has a power series expansion, and these coefficients are traditionally called tau of n, Ramanujan's notation. So you just integrate term by term, forgetting the 2 pi I to the 11th, and so you can do that. But even if there were a constant term, of course, you can integrate 1 11 times, getting a polynomial. So you get this function which has this derivative, and now we make the little computation. that if I take this thing in weight 2 minus k and differentiate it, then by Bohl's identity, that's the same as if I took the k minus first derivative of f tilde, which is f, in weight k, slash gamma. But since f's a modular form, this is f, which is f tilde, the k minus first derivative. And therefore, we have two functions with the same derivative. And therefore, we find that the two functions are the same up to a function whose k minus first derivative is 0. In other words, it's simply a polynomial of degree k minus 2 in tau. Sorry, RF of tau. Well, simply RF. OK, so in this way, we associate to, so let me make a notation. Let Vk be the space of polynomials. So this is polynomials in tau of degree.
RF depends on gamma, right? RF depends on gamma.
Thank you very much. RF absolutely depends on gamma. Thank you very much. Indeed, it does. It's a cocycle, in fact. So here I take things of degree at most k minus 2, and here the action is in weight 2 minus k. So if I have a polynomial, r slash abcd, just by the definition that I gave you of tau, is c tau plus d to the power, now it's plus k minus 2 times r of a tau plus b over c tau plus d. And of course, that's again a polynomial. So this is the usual finite dimensional representation. And so we have this map from modular forms. This works for any group at all. We have a map to Vk, but actually, as the comment that I just made, it's of course maps, and actually it goes to, this is a cocycle, sort of automatically. It's a cocycle of gamma with the coefficients in Vk, and its cohomology class is then something interesting. So if I do this explicitly for delta, taking delta tilde, I'll forget the 2 pi I. Of course, this still works with that factor. So if I take delta to be this, then you see immediately that in the case of SL2Z, there are only 2 standard generators. That's all you need, because a cocycle is determined by its values on generators. And with this choice, it's already invariant under the first one. That would not be true if I took a non-cusp form, because I said if f had a constant term, 1 or something, then when I integrate 11 times, I would have a polynomial starting with tau to the 11th, and it would no longer be translation invariant. But anyway, I would always get something, but here it's just 0, the cocycle associated with that. And therefore, for that very reason, here I really don't need to the gamma. So when I talk about SL2Z, I'll think of parabolic cohomology T, which is this generator, goes to 0, and the other generator, just as S, goes to R, F, which is RF. S. So I'll only write RF, which is why I wrote it before. I wasn't thinking. So in the case of SL2Z, we have a nice map, R, which goes from, well, since I'm doing it parabolic, let's say from cusp forms into Vk. But actually, they're going to go on into a certain subspace, Wk of Vk, which I'll define in 1 second. Namely, if you look at this, then you find that R delta is just F tilde slash S minus 1, where I've extended the slash operation of the group algebra just linearly. So that's the definition. So obviously, if you applied S, which is an involution of that, it would change the sign. And so you have one automatic relation. The polynomial you get is certainly antisymmetric under S. But we also find that if we take the element, I guess, Ts, or maybe St, I guess Ts, which is order 3, maybe I'll do that calculation. It's, of course, familiar and very easy. Then if I compute R...
Sorry, you also about delta is delta theta, which comes after that, not f theta. Last line.
This is surely correct. Well, the delta, f is delta, but otherwise it's, well, that was my example. This f was delta, yeah. But anyway, the formula is correct. So let's think, I mean, I can certainly do this without looking, but let's take my f tilde. It could be actually for any f. I don't know why I was taking delta. It makes no difference. If I take f tilde slash u, then that's slash ts, but this is a group action, so I can put t slash s. But f tilde for cusp form is invariant under f. So you just have f tilde slash s, which is f tilde plus this polynomial. And now I do it again. And so I get f tilde slash u plus rf slash u. But by what I just did, that's RF, F tilde plus RF plus RF slash U. And then finally, if I do it a third time, then, well, you can imagine how it goes on. But on the other hand, U cubed is the identity. And so this is F tilde. And so you have this second equation that this thing has to vanish. So WK is the set of polynomials of degree at most k minus 2, which are annihilated by, well, I could have just written the intersection of two kernels. It would have been shorter. It's annihilated by both 1 plus s, where s is the standard element of order 2, and 1 plus u squared, u being the standard element of order 3. Actually, it turns out this is a nicer version of the function. You can write it in a single equation which takes care of both of these. This is the Lewis version. It's simply r slash t plus r slash t prime, where t is as before this, and t prime is the transposed matrix. And then it's an exercise that each of that equation implies the two others, and those two imply this, at least if k is bigger than 2. Okay, so we have a map into that space. And now this space, well, it is much smaller dimension. The original space is dimension k minus 1. This is much smaller dimension. So let's look at some examples. If k is 4, 6, 8, 10, or 12, or 14 rather, then WK, you just do it on by hand. It's a very easy computation. You look for all polynomials that do what I just said, and you find that there's only one. This one works for every k, but for these k's, that's the only one that works. But for k equals 12, if I write the odd part and the even part, so you can split the polynomials into even and odd, and each part is still in WK, then here you still have x to the 10th minus 1, but you have a second one, x to the 8th minus 3x to the 6th plus 3x to the 4th minus x squared, which is, of course, factors as x squared times x squared minus 1 cubed. And W12 minus is one-dimensional. It's factors. It's 4x to the 9th minus 25x to the 7th plus 42x to the 5th minus 25x cubed plus 4x, which again factors is x times x squared minus 1 cubed times x squared minus 4. I know that x squared minus 1, x squared minus 4 also factor, but I'm not going to bother. So, okay, so you have this. It's just a simple computation. And so you find that, for instance, r delta of tau, I don't know why I called it x and it was tau before, but this has to be, well, I'll just do the positive part. It'll be omega plus times something. It would a priori be a combination of this and this. But by Hackey operator, so this is just from the general Eichler-Shimura-Manning theory, one sees that the two parts, the even and the odd part, will be separately, because of the action of the Hackey algebra, are separately defined over q bar in general, here over q. And here you get the 691 that we have seen many times. I hope I'm doing it right. Minus x squared times x squared minus 1 cubed. And similarly, of course, r delta minus there's no issue, is just omega minus, this is for delta, times this other polynomial, 4x to the 9th minus so and so, except that this should have been tau everywhere. Okay, so here, and so we get, in the end, just two numbers, and these two numbers, well, one is real and one is pure imaginary, but anyway, there are two complex numbers, known in this case both to be transcendent, and you should think of them as the exact analog of the two periods omega 1, omega 2 defining an elliptic curve, except that if you divide C by this lattice, you get something which is physically an elliptic curve over C, but not at all algebraic. I mean, its J invariant will be transcendental, and it's actually some motivic thing of higher weight.
Where's this number, 36 over 691 came from?
Oh, that's a fact. So that's just a fact. I didn't prove it. What I said is that using well-known theory of Eichler-Manning-Shimura, one knows that the Hackey operators act. And from that, the Hackey operators, that action can be pushed over here. So here one has Hackey operators, which I didn't go into at all. They fix, well, it's a one-dimensional space. So, of course, delta goes to multiply itself, which is minus 24. And they also act on this space. And the unique vector with eigenvalue minus 24 is that one. So it's automatically a multiple. So it's very easy. But I didn't prove it, indeed. I just said it was true. OK, so that's to get the thing off the ground. And the reason I mentioned this, well, I mean, it's, first of all, in case anybody hasn't seen this, it's so nice and such a part of basic, beautiful number theory that everyone should have seen it. And secondly, it plays, well, I'll use something of it later, but there's also the connection which hadn't, I think, been previously particularly mentioned, at least not very explicitly in the conference, but now was in Francis' talk. I mean, he said much more, but somewhat in shorthand, so that there's a connection. Well, he mentioned a much deeper connection, the conjecture of Broadhurst and Kreimer in his own work on the connection of higher depth multiple zeta values to modular forms. But there's an easy one which is known for a long time. Certainly I've known about it for 20 years, and so have many other people, that if you go between double zeta values, which is among multiple zeta values, these are just depth 2, so zeta of Rs, then there's a very intimate connection between this and modular forms. And so I have a paper with Herbert Gangel, who's here and spoke, and Kaneko and myself a few years ago, where we studied this. There had been an earlier very brief thing by me where I'd sort of written something down. And there are many, many connections. I mean, the paper is quite long, like 40 pages. There are about 8 different cross connections. It's actually very confusing. But I'll just give you an example. It turns out that you always, in even weight, you always have one kind of universal relation that if you take all of these double zeta values with both arguments odd, and I'm using the same convention as Franz, even though he said nobody does, but he was wrong, except that I forgot one term. So these are all the convergent ones. 11,1 would be divergent. And then this thing, it's well known that the sum of all the double zetas, or all the zetas of any fixed depth, is simply zeta of k. But here this is actually 1/4 or 3/4, can't remember which, times zeta of 12. But I don't care. It's some rational multiple of pi to the 12th. So that relation is true in weight 12, but it's true in every weight. If you add all the convergent double zetas, Rs with R and S both odd, then you get a multiple of pi to the 12th. But for the first time, I think it was Herbert Gangel who noticed that first, for the first time in weight 12, you get a new relation. And I mean, I'm just putting it modulo pi to the 12th. In the paper, we give a more precise version, which includes the coefficient of pi to the 12th, but that's also very much connected with modular forms. But I'll skip that. So here's the relation you find in your database, or just numerically. And of course, you can prove it by double shuffle relations. But the question, once again, is what is the meaning of these coefficients? And so the meaning is very simple. If we take that R that I wrote before, but I'm going to take just the part, the non-Eisenstein part. So this thing, remember, was an element of W12 plus, but it's not part of the image of delta because the Eisenstein series would have given the tau to the 10th plus minus 1. So I'm always using x because I'm used to it. So if I call this R of x, I mean, I could add the Eisenstein part too and put in the stupid 36 over 691. But if you do what I'm about to do for the x to the k minus 2 minus 1, you will always get this boring relation. So I might as well subtract it off and just work on the new one. So this is much simpler to write. Well, if you do this and you write down now R of x plus 1, that's the general recipe. So it's some new polynomial. Uh, 38, if I read correctly from my notes. And now if I do this and I keep just the even terms, so again, that's just a recipe, then you find that up to a factor, let me multiply by a factor, which of course won't change the relation being true, but it'll get rid of denominators. So I multiply by 1260. Then you see a coefficient here, which is 1260, which just happens to be binomial coefficient 10 over 8 times 28. And this one just happens to be 10 over 6 times 150. And this one is 10 over 4. So these coefficients, if I divide them by the corresponding binomial coefficients, then you see the 28, 150, and 168. And this works, of course, then in every weight. So in other words, there's a direct relation between the part of the beginning of the mysterious rational linear combinations, rational relations among multiple zeta values and modular forms. You see it very clearly and in a very nice way on this level. As I said, there are actually other relations. This uses only WK plus. There's another thing involving WK minus. That was sort of the first of my, I wanted to give a potpourri lecture. So that's the first part of the potpourri. It's just this, this thing. So I think you've seen these numbers. I'll erase rather than, you know, they say to talk softly and carry a big stick, but I'm a little afraid of the stick. So I prefer carrots. Okay, so then I wanted to go on now, think of periods of elliptic curves. So I already said that. We're now going to think of elliptic curves. And then I already made this comment that then the J invariant, so if I have an E, a family of elliptic curves, depending, say, rationally on some parameter t, then J of ET, if I think of this as corresponding to some C over some E tau, tau will also depend on t, then the fact that the J invariants have to be the same tells you essentially that t is supposed to be a modular function of tau. And I mean, that's not quite a proof, but it is true. And as I already said, you get a differential equation. So the name of the game is this. So the periods of this, remember we had the period lattice, which was the set of integrals of dx over y over the first homology, and I chose a basis for that. So locally, this basis makes perfectly good sense. These become functions of t. And now what you find is, well, sort of by definition, omega 1 divided by omega 2 will be tau, at least one version of tau. If I chose a different basis, I would change tau to a tau plus b over c tau plus d. So that's sort of what the tau is. And now that means that we have something absolutely canonical. If you have, so a and b here, as already said, are going to become modular functions. Those are modular forms of weight 0, maybe poles somewhere. But they're there, so a of t of tau and b of t of tau. If I think of t as becoming a function of tau, maybe it's not yet quite clear how to do that, then these will be modular functions on some group, so they're invariant, under some group gamma, now of, in general, a finite index in SL2Z, or maybe sometimes you make it a little bigger afterwards. It may take a commensurable group. So if we think of this, let's assume, sort of conversely, that you had a modular form of weight gamma, of weight 1 on gamma, on this group. Well, then, if I think of f of tau, that's the correct order is this one. If I think of the pair, f of tau and tau f of tau, and the thing they span, I'm sort of starting at the other end with the modular form. Well, obviously, that's a lattice, because tau is always linearly independent of 1. Let's say f of tau is no zeros to keep things easy, and it's moving around. And it's, of course, got the J invariant equal to J of tau. But now the point is when you apply f of gamma tau, then f of gamma tau will go into, up to a constant, into the same lattice, because f of this will go into f of tau, which is c tau plus d, since I'm in weight 1, times, again, times f of tau. Excuse me, I did this wrong. But of course, f of tau times tau will go into a tau plus b over c tau plus d times the same thing. And so you see that this is simply the same lattice. So this lattice is preserved, and conversely, this lattice which is preserved then can be written in that form. So the bottom line is that not only is the ratio of these things tau, but the denominator, t, becomes, in the upper half plane, a function which is a modular form on some group. Okay, and there are lots, and this is the famous Picard-Fuchs differential equation for this family of elliptic curves. Well, there's a more general statement. That's sort of a geometric way of saying it, but you can do it purely algebraically. If you have any group of all in anything, it doesn't even have to be holomorphic. It could be meromorphic. It could have even some singularities. You do need k positive. And if you have also a modular function, so let me write the variable tau to emphasize it. If I have on the same group a modular form of some positive weight k, and a modular function, which is the same definition as before, except there wouldn't be any, so I have to drop the condition of good growth at infinity and allow poles, either finite or at infinity, then I can attempt to write f of tau in terms of t of tau. I mean, locally, tau goes to t of tau is invertible, so I can invert this. Of course, I can't expect to do that globally. This is a t, and it looks like an f. If I move around, if I send tau to gamma tau, then t doesn't change by definition. It's a modular function. But f does change by c tau plus d to the k. By definition, it's a modular form. So this can't be true globally, but it's true locally. And the failure globally exactly means that phi satisfies a linear differential equation, let's call it L phi equals 0, of order k plus 1. And now there's a slight caveat. So it's, let's say, the sum 0 to k plus 1, ai of t d to the I by t d to the I. These functions in general are only algebraic. They don't have to be polynomial. It's only an algebraic differential equation because actually when you do the whole calculation, what you find is that they're modular functions. And any two modular functions are algebraically related. So ai is an algebraic function of t. But in simple examples, the genus of the curve h modulo gamma might be 0. And then this map t, if I compactify everything, this map might be an isomorphism. Then it's called a Hautes module. And then, of course, it's just a rational function of t. And clearing denominators, I can assume it's polynomial. So in the interesting case, it's a polynomial. And the cases that one usually writes down because they're somehow much prettier. Now, I guess I do have to use the stick both. Okay, so we have this very basic fact. I just wrote it as a fact. It's not quite obvious, but not very difficult and very, very basic. So I say it's so important. It's an absolutely major thing in number theory that many people don't have present in their minds. It's that every modular form expressed as a function of a modular function locally is the solution of a linear differential equation with algebraic or polynomial coefficients, finite order. Well, in fact, of order exactly k plus 1, where k is the weight. So let me mention a famous application of that. Now I'm checking my watch. Usually I worry about running out of time. Then I'm worried more about running out of material. Okay, maybe it won't quite happen. So let me give an application, which again is very well known, but I wanted to say a few things about them. They're also old, but it's such a mixed audience that surely not everyone will know everything. So this is the proof that Apéry gave in, I think it was 1978. I didn't look it up now. It was roughly then. That Zeta of 3 is irrational. So his proof was, the basic step, what he proved, was the following. Well, I'm not yet ready to state the theorem because I need a little notation. So he wrote down he actually proved also that Zeta of 2 was irrational. Of course, that was very well known because Euler proved it was pi squared over 6, and then various people after Euler, but well before Apéry, had done the rest. But the proof is very similar in the two cases. It doesn't work for higher zetas. And I'm going to talk for the moment about Zeta of 2 and come to Zeta of 3 in the moment, just to have simpler equations. So Apéry, for the Zeta of 2 proof, wrote down the following recursion. And so let's look at the solutions of this. It's a three-term recursion. So if I specify two successive values, then I've done everything. So let an be the Apéry numbers. Well, if you look at this, you see that there's up to a constant, a unique solution where this is true for every n, where I assume that the negative index un's are 0. Because if I start with u0, then I get 0 equals 0. So that's good. If I take u1, I find that u1, n is 0. Sorry, n is 1. So u1 is equal to 3 times u0 plus 0. So if I normalize to start with 1, then it'll continue 3. And then everything is well defined. And that's the only solution for which this recursion is true for every n, positive, negative, or 0. Well, I extend to 0 on the left. So the sequence, you can obviously compute as many as you want. The sequence starts like this. But then you can take a second sequence where you start with, you might as well start with 0 by subtracting that, put 1. So the recursion will be false for n equals 1, but you assume it from now on. So then you get also a bunch of numbers, which, when you compute them, the first couple are this. It's meant to be 65, 85 over 16. And so Apéry proved three utterly remarkable things, especially the way he proved it was particularly remarkable because nobody had any idea how he found any of this, and he never really explained. An is always an integer. You see, a priori, if I start with two integers, then un will be 1 over n factorial squared times the integer, because at each stage I divide by n squared. And so that's an awfully big denominator, but as you see in the first few values, they're integers. In fact, he showed that that always happens. And he showed that by giving an explicit formula for an, which is obviously an integer, but not at all obviously a solution of the recursion, nor was it obvious how he found it. Okay. The next thing he showed, well, the bn's, as you see, are not integers, but he showed that the denominator is much bigger. Instead of n factorial, which is the product of 1, 2, up to n, you just take the LCM of 1, 2, up to m, which grows like e to the n by the prime number theorem. So it's only exponential growth rather than factorial. And as a result, that means that bn is, in some sense, nearly integral. And thirdly, well, what he didn't show, I mean, he also showed, but that's trivial, is that since there are only two solutions, there's a big one and a small one, any solution has to grow here like 1 plus the square root of 5 over 2, so to the power plus or minus 5n. That's very easy. Just take the leading term. You have 1, 11, 1, and the equation x squared minus 11x minus 1 equals 0 has two solutions. So any solution grows like either 1 plus the square root of 5 over 2 to the 5n, or the inverse of that. And so an and bn are both obviously growing, but then some linear combination is very small. So what is easy is that if this is the limit, it exists, and the error is actually 1 plus the square root of 5 over 2 to the power minus 10n, which is incredibly small, much smaller than the dn squared, and that therefore immediately implies the irrationality of the limit. But the problem is it's not at all obvious what the limit is. And so what he showed is that the limit is 1/5 zeta of 2. Sorry?
No, yeah, in the case of Zeta 2.
This is all for zeta of 2. I said it. This is all for zeta of 2. So here it's zeta of 2, and this is 1/5 zeta of 2. I mean, I can give the other one in me, but I might as well give it now since the question was raised, and I wanted to talk about it a bit later anyway. So for zeta of 3, this story is very similar, but now the equation is slightly different. It's 34n cubed minus 51n squared plus 28 minus 27n minus 5 times un minus 1 minus, this time, n minus 1 cubed un minus 2. And you have an exactly similar story, an and bn. So the one starts 1, 5, 73, 14, 45. And the other starts, again, 0, 1, 117 over 8, and 6, 2, 5, 3, 1 over 36. And then in that case, he shows that an is an integer, dn cubed. So this time you get the cube. You see an 8, and this is illegible. Yes, but I don't want to. I want to just talk this. So let's. Unless something I already said was unclear, I don't want to digress because I'm going in a certain direction and don't want to discuss. Also, I don't happen to remember I didn't even get what kind of an equation that is. This has to do with the Frobenius method and Perron things, but I don't even know the terminology. Anyway, it's not what I want to say. This is all very, very old anyway. So it can't be, this was 216, which is 6 cubed. So you see this dn cubed. And this time bn over an tends to 1/6 zeta of 3. And as I already said, this was very rapid. I mean, I have given somewhere a numerical value, not that you need it, to impress you. And anyway, I seem to have lost it. Here it is. So just as an example, B4 over A4, I'm in the zeta of 2 case, so it really goes very fast. It's 0.32898681 and so on, and 1/5 zeta of 2 is 0.3289868113. So, it's the convergence is incredibly fast. So the question is, so as I say, he had a very mysterious proof of this by sort of just magical formulas that he had discovered and that people didn't know how it found them. Thank you. How do I get there like this? And then a few years later, Fritz Burkers saw that this story fit in perfectly to the story about differential equations. So, the usual problem everyone has had. So there turns out in both cases to be a modular interpretation. I'll give it briefly. So what you do in the, let's say in the first case, you take, so this is Fritz Burk's, many years ago already. Observe that if we take t of tau to be q, I already have the product 1 minus qn to the first. That was my eta, well, with the q to the 1/24th in front. Now I take a very famous function of Ramanujan. So this is a modular function of weight 0, so a modular function on some group, gamma 1 to 5. And I also have a second function, f of tau, which is some Eisenstein series of weight 1 on that same group. So on SL2Z, you don't have anything in weight 1, but on this group you do. And you can also write that, if you want, in terms of eta and this function I already have. So it's eta 5 tau to the 5th over 8 of tau times t of tau, where t is the thing I just wrote, and that is a sort of a canonical square root. So you have these two modular functions, and this is weight 1, that is weight 0. So this one starts q minus 5q squared plus 15q cubed, and whatever it is, 30q to the 4th. And this one starts 1 plus 3q plus, it is much smaller coefficients because it's holomorphic. It's an actual modular form, an Eisenstein series. So if you write f like that, you just get an expansion. But now what Burk has discovered is if you do just what I said before and write f, not as a power series in q, but as a power series in t, which is an invertible power series in q, so I can do that, then what you'll get is something with admittedly much bigger coefficients, but they're now exactly the Apéry coefficients. And so the general theorem that I told you before, which tells you that any modular form satisfies the differential equation, you just apply it here. It's explicit. You get the differential equation. That gives recursion, and you discover that the recursion is indeed Apéry's recursion. And therefore, you've proved something. You've proved the integrality, because this is obviously all integral. But that still leaves you with the second one, the b, and also the limit being zeta of 2. And so that also was found by Burk. So the story is very nice. So what I just said is that if I take these two power series, with the 2, I'm doing zeta of 2, but it's equally in the other case. I can write down the modular functions there if you want. They're on a different group, on gamma 0 star of 6. If I write down these two power series, then remember we have this differential equation which annihilates A. For B, B was only a solution of the inhomogeneous recursions. That means that LB is no longer a solution of the original equation, which would have a log singularity, but if LB equals 1. And so that means, so we know that the solutions here, I mean not in power series, but the solutions to the kernel of L, we know corresponds after I go from t to tau in the upper half plane. We already know what they are. One of them is f of tau, and the other is tau f of tau. So you notice that the tau is, log q. So the second one is a log singularity. But how about this one? Well, it's very easy once you've had the idea, which the solution here, this b of t of tau, turns out to be nothing else than this remember, is an Eisenstein series of weight 1. You take another Eisenstein series, I hope I remember correctly, 3. So I'll just call it g. And now I multiply f of tau, not by g of tau, that would be something of weight 4, but of g tilde of tau, this Eichler integral that I told you about. So now what happens when you do monodromy? So I go around and come back. Then when I go around and come back, my tau has gone into some gamma tau. Then f of tau has gone into c tau plus d times what it was, times f. But g of tau is replaced by, well, g of tau is nothing, but g tilde of tau is replaced by c tau plus d. It's in weight 3, and I went from weight k to 2 minus k, so it's minus 1. So it's minus 1 times g plus something times tau plus something. But now if I multiply these two equations, then the c tau plus d goes away, and I find that f times g goes to f times g plus something times f times tau plus something times f. But this was exactly the kernel of L. And so the ambiguity, sorry, f g tilde. So g tilde is not a modular form. It had this ambiguity of the period polynomial, but it has the ambiguity, which is just adding a polynomial in this case of degree 1, in general degree k minus 2 if k is the weight. And so the ambiguity in this product is f and f times tau, which was just the kernel. And therefore, if I apply L to f g tilde, it has no ambiguity. And so it's a well-defined function, and so that means that this is a nice power series, and then you check easily that it's the right-hand side. I mean, that function turns out just to be 1, and so we have the solution LB equals 1. So that gives you this interpretation, and now you see you're done again, because G has some coefficients, C n q to the n. These are integers, because it's multiple forms of integer coefficients up to a fixed denominator. But now remember, to do the Eichler integral, I had to integrate k minus 1 times, where k was the weight. The weight here is 3, so I have to integrate twice. So therefore, the nth coefficient is a denominator exactly 1 over n squared. When I multiply by f, which is some bn q to the n, also with integer coefficients, then the nth coefficient will be a linear combination of c r over r squared times b n minus r, and so it'll have a denominator at most dn squared. So the second part of Apéry's theorem becomes obvious, and the last part also becomes obvious because the limit, as n goes to infinity, of an over bn is just the same, bn over an, is just the same as the limit of the ratio of these two power series solutions at their first singularity, which I already told you what it was. It's, I have no room to write it. It's square root of 5 minus 1 over 2 to the 5th. So if you take the value of these two power series, they both have a singularity. They both plop at the same nearest singularity, 1 over the radius of convergence. But that point, this turns out to be exactly t of 0, this modular function. So this is simply, since b is f times g tilde and a is f, this is just g tilde of 0. I mean, it's the limiting value. And so this is known because for Eisenstein series, it's very easy to compute the transformation law, including the period polynomial. And so we know what it is, and it turns out to be zeta of 2. And the same for zeta of 3. So you have this very beautiful modular explanation. Again, this is ancient, but it's so pretty that in case anybody hasn't seen it, I want to have at least shown it. Now, yes, of course.
What about for zeta 5?
For zeta 5, no, if you can answer that. I can't, then you'll become very famous. It doesn't work. Many things go wrong. You see, I didn't tell you what these modular functions were. I told you t and f for the first one. They're still there, so maybe I don't have to. T is this very random thing, q times the product 5, n over 5. How do you find that? And f is this completely random thing. That was for zeta of 3. For zeta of 2, I remember the functions, so I can give them to you, except one of them I don't remember which way up it is, and I think I do. It's 8 of tau, which remember is the 24th root of delta, times 8 of 6 tau, all to the, over 8 of 2 tau, 8 of 3 tau, all to the 12th. So this is a modular form of weight 0, meromorphic on gamma 1, gamma 0 star of 6, it's called. And f, in this case, is 8 of 2 tau to the 7th, 8 of 3 tau to the 7th, over 8 of tau to the 5th, 8 of 6 tau to the 5th, which is a modular form this time of weight 2. So you get a third order differential equation on the same group. And there's absolutely no way to guess that. That's what I'm trying to show you. This is just a complete miracle. Why is this on gamma 0 star of 6? Why is the other on gamma 1 star of 5? And why should there be one in general? So there's no reason even to think, in some sense, that you can do anything. Well, in fact, you always could do something, because you pick any group, any f and any g, such that the weight of f is some k, one bigger than the order of the differential equation you want. The weight of g is 2 bigger, so that when you take its Eichler integral and multiply that, that's weight 0, and then you do the same story, and you'll get something. But it'll almost never give as a limiting value anything of any interest. So if you prove irrationality, you'll get the irrationality of some unknown number. And what's more, you never get irrationality, because there were a series of like 15 miracles here that I skipped. Remember I said that dn grows like e to the n. So dn cubed, well, dn squared, for the zeta 2 example, grows like e squared to the n. And then I square it. And luckily, e squared squared is a little bigger than the fifth power of the golden ratio. But if it had been smaller, you would have just got excellent approximations. So there was just a series of lucky accidents. I can assure you that I and everybody I knew for 2 years after it's proved tried very hard to make it work for zeta 5. Everybody gave up, and it still hasn't worked. It's still not known if zeta 5 is irrational, the results of Riefenwald and others saying that there are linear independences. But there's no guarantee that you can find. You see, it's easy to check that this is true. If I write down this f and t, I can tell my computer to find the differential equation and check that it's Apéry's. But if I give him Apéry's equation, well, actually, I can also tell my computer, in the paper I'm just about to report on, and I did that, look if there's a modular form that works. But there almost never is. So that's, in fact, just what I wanted to come to. I wanted to talk about this experimental paper I wrote, well, actually, many years ago and published a small number of years ago. So in Apéry's equation, let's just take the zeta 2 one for the moment. there was an 11, and the other 11 has to be the same, so I'll call it, again, 11. Well, let's write it more. So here would be the Apéry equation. In that case, AB and minus 2, AB and lambda would be, in his case, 11 minus 1 and 3. Okay? So that's the equation that we just had. And Fritz Burkers had looked at this equation for some p-adic reasons as a family, said, what happens if you take other values of a and b and lambda? Just what you were asking, do you get something, are you lucky? So I looked, and I just looked, there's an obvious rescaling. If you multiply un by alpha to the n, you can replace a by alpha a, lambda by alpha lambda, and b by alpha squared. B, so you might as well, I want to get rid of that. So up to that rescaling, I looked at 10 to the 8 triples on the computer, not by hand, AB lambda, and for each one, I just started this recursion, a la Apéry, and looked whether I got integers. Well, very soon you get a non-integer. Occasionally it keeps going, and when you get to 30, you've had 30 integers, you print it out. You got integers, only seven triples out of 100 million worked. So this is really a miracle. That's what I wanted to emphasize. It's very, very rare that you get this integrality, and in fact, Maxime has been telling me amazing ideas according to which the set of sequences satisfying a polynomial recursion with this integrality has some very, very deep motivic and very conjectural meaning. But anyway, here, just experimentally, it's extremely rare. So I might as well give you the table just for fun. Well, the last one's kind of a little boring, but here it is. OK, so if you take these values, then you get integers, and they're sort of minimally scaled to give integers. So, and all of them, and all 7, so first of all 7 were modular. In other words, for each one, this was just experimental, that the Apéry phenomenon worked, but then if one tried the Burkers method, and I found a nice way to check if a function is modular sort of numerically, they were all modular, and then in fact, using a result of Beauville, all modular, I can just reverse the grammar. All modular are 7. So all modular equations, in other words, all differential equations you can get the way I said, start with a modular form and a modular function. If they have this form, well, that happens exactly 7 times. So in other words, the conjecture that these are the only 7 with integrality, since these 7 are exactly the modular ones, is the same as saying you will never get this mysterious integrality unless things are modular. But I should very much avoid giving you the impression that that's always true. So there are higher equations. Well, in particular, there are families called Dn, D2, D3, D4, introduced by Steenstra and Golishev 5 years ago or so. This family is the D2 family. D3 has a few more parameters. This has 3 parameters, and so on. And in each case, it's very, very, very rare that you get this integrality. And there's supposed to be a geometric interpretation. So the n equals 2 case, which is the case I talked about for the Apéry case, is families of elliptic curves. That would be, that corresponds to k equals 1. So if this is called dn, n is the order of the equation. But remember in the theorem I told you, which is certainly not mine, it's an ancient theorem, the order of the differential equation is always 1 more than the weight. So if the weight is 1, you get a second order differential equation, like Apéry's for zeta of 2. Then for k equals 3, for k equals 2, so weight 2 form, that means a third order differential equation. That would be like Apéry's equation. To see the order of the differential equation, you don't look at the length of the recursion, but the polynomial coefficient. So it's 3. And so this corresponds, well, conjecturally, because if it corresponds to a family of elliptic curves, for the reason I explained to you, the solution is modular. And as I also just said, we have no idea if they're modular. We only know that up to the first 100 million, there aren't any integral solutions that aren't modular. And so if we already don't know it here, you can be sure we don't know it here. So maybe there are other mysterious ways. In fact, there certainly are. In higher weight, that's what I wanted to say. It's not only modular, but what it should always be, conjecturally, these are general conjectures, maybe Dwork, Grothendieck, I don't know quite who, they should always be Picard-Fuchs equations, or if you prefer Gauss-Manin connection equations, there should always be a geometric meaning. So if you have any family of varieties, it doesn't have to be elliptic curves, or there doesn't have to be anything modular. There are periods, and the periods always satisfy differential equations, and because there's a lattice that's preserved, the integral homology, roughly, the monodromy group always reduces to SLN Z, and you get some nice, deep down, there's integrality built in. So the general conjecture is that everything you'll ever see with this integrality always comes from geometry, from some family of varieties. But so So the families of is supposed to continue forever. But here, these are K3 surfaces. I mean, this is one dimensional, this is two, and the next time it'll be Calabi-Yau threefolds. So here there are roughly half a dozen, as I said, interesting examples. Here there are about, I forget, 30 or roughly of that order, of which quite a few come from that by kind of lifting. And here there are, I think, currently something like 700 or 1,100. So Dieland and von Straat and Almquist are the main people who keep track of that. So there are web pages. And there are many, many known examples, all believed to be geometric, many of them known to be geometric. But these are always modular. These here. And these are also all modular, but these are, I think, never modular, but certainly usually not modular. So it's still geometric, but you can no longer, it's a family of something, but it's no longer a family related in any nice way to things like elliptic curves. So that's something I wanted to have said. And now, I'm going to end up going over time. No, I'm not, because I'll just stop. So I wanted to say then a very little bit about this last case. So there's been a lot of studies of this. There's a recent paper by Masha Plasen, Vasily Goleshov on the D3 case where they're modular and they show that all modular solutions with a certain multiplicativity property are the conjectural complete list. So there's partial information. It's all very, very partial. I mean, this field is not at all, we don't understand many things. I mean, I showed this, of course, the one of interest to physicists for mirror symmetry, and an example completely boring from the point of view a la Apéry, because these coefficients are trivial as coefficients. They satisfy a completely trivial recursion, two-term recursion, because it's just hypergeometric. But this is the famous thing associated to the quintic mirror symmetry, and that absolutely fits into this and into the mirror symmetry story. But it's not modular. The monodromy group reduces from GL4Z to the symplectic group, but in no way to what it should be here, which is the symmetric cube of SL2. So it can't be modular. Okay, so just to finish very briefly with something that's new, or at least actually even not all that new. I wanted to talk about polylogs too, but now I see I really did run out of time, despite everything. Let me just mention some, Vasily Goleshov is here and has extremely exciting ideas, which I only a quarter understand, and even if I did, wouldn't have time. But let me just say a few words. In a particular case that he told me about, and we did some numerical work and a little bit of theoretical work. So let's consider Fano threefolds with one-dimensional Picard group, or actually just first a homology group, you can say. And these have been classified via Skovsky.
It's as always implicit in Maxim's word.
Okay, whatever, well, yeah, but that's hardly worth saying because, as you say, that's as always. So, okay. These have been classified. Yeah, I mean, I'm very well aware of this phenomenon, but too aware, all too aware. Okay, 17 families. And so there are correspondingly 17 equations. And there are also 17 nice things on the modular side that you can uniquely produce from sort of modular data, and the things match up. That's a nice story, which is, to me, a complete mystery, and I won't talk. But let me just say that there's then something just to you or to you and Mellett called the gamma conjecture, which roughly, if you take one of these Fano threefolds, you use, so we take the cohomology of it. So this is if I take just the algebraic part in this case, it's something four-dimensional, and we'll get a fourth order differential equation, but not in any obvious way. This is from quantum cohomology, from Gromov-Witten invariance. Gives a fourth order differential equation. But this is not of the Apéry sort. This is a little different. And I can give, for the only example I'll talk about, it's the one called, the family called V12. So if you want to know, the diagonal Hij are all 1, and H12, and of course H21 are 7. The others are 0. So C1 is 12 times the generator. So for this particular thing, this differential equation corresponds to the sum, the solution of it, so it's the thing satisfied by this power series. You take the Apéry numbers for Zeta of 3. So for the second family I gave with this Zeta of 6, gamma of 6 example, but you don't take that function, you divide by n factorial. So of course it still satisfies the recursion. So it satisfies, let's call this phi tilde. And of course now there's some new differential equation. But now it's fourth order. Remember before it was third. And so you have four solutions. let's say A0, which is this one. Let's call it A0. And then, of course, as usual, the Frobenius business, you have A0 log plus something holomorphic, and one with the log squared and one with the log cubed singularity. And now you can look at these functions, and this time you don't have to go to the nearest singularity, which was the golden ratio to some power, because now you can just go to infinity. There aren't any singularities except at 0 and infinity. And so you can take the limiting value of this, and this gamma conjecture, which has a deep background, which I certainly couldn't explain even if I wanted to, makes a very specific prediction and tells you in this case the 4 numbers that you get. And they are 1 minus gamma, Euler's constant, gamma squared over 2 minus 3 halves zeta of 2. And for 3, it's minus gamma cubed over 6. Well, you can guess the gamma part, plus 3 halves zeta of 2, plus 5 halves zeta of 3. And so that was the prediction of this gamma conjecture. And that I was, so Vasily showed me, I was able to prove that. So this is a theorem. These are the limits that are predicted by these ideas coming from quantum cohomology. But it's actually a little interesting. These are the 4 Frobenius solutions. But actually the Frobenius solution, which you get by varying very slightly, replacing t to the n by t to the n plus epsilon, they're actually infinitely many. You actually have an aj for every j. It's just, of course, you can't have more than 4 solutions of an equation of degree 4. And it's simply that this is 0 if j is less than or equal to 3, but if j is greater than or equal to 4. So it will start, this one will start a0 times log to the j over j factorial, log jt. Now it's no longer homogeneous. Exactly like in Apéry's story, when j is 4, or 5 in this case, 4, you'll get 1, and then you'll get log t, and so on. So here you get a series of infinitely many solutions. And sort of amusement, it's very easy to compute these limits numerically. And so I computed, I don't know why I changed n to j, I computed them a lot further, the first 9 to very high precision, and you didn't need any data mining, it was quite easy. They were all combinations of zetas, so the 9th one involved zeta of 9. So, well, it was even slightly better. I already said that, of course, everyone can see this gamma, but in fact, if you go a little further, you'll get gamma times zeta of 2, and actually the statement, if I call this constant Cj, then what you find is that the log of the sum Cj x to the j, apparently it starts, minus gamma x, and then whatever it is, zeta of 2, minus zeta of 2 times 3 halves x squared. The gamma only occurs once. So this is all polynomials in single zeta values. So I have no idea either if that's true in general, nor if it will, there are 3 possibilities. It's completely wrong, it's completely true, or it's later multiple zeta values, but at least up to degree 9, there weren't anything multiple. And there's obviously a lot going on very related to periods. So this was a totally disconnected lecture, but at least I'm going to end. That's the good part.
Questions? Since people are thinking about questions, I have a question.
Okay.
The new demonstrations about zeta of 2 being rational.
They aren't new. This was within 3 years after Apéry's. They're from 1982.
No, I understand the
Yeah.
logic. How through this reasoning you came to the conclusion that zeta of 2 were irrational? Because you were looking for this.
Oh, that I didn't mention. Oh, sorry. That goes back to Lambert, maybe Euler. We simply had a series of approximations. Remember, I gave you B4 over A4. And the denominator, so it's a fraction. So it has a numerator to denominator. The denominator is A4, because that's already there, times, at worst, D4 squared. Right? But then, remember, so in this case, we had a constant, which in one of the cases, it was 11 plus 5 squared of 5 over 2, which is the golden ratio to the 5th. And then I said that any solution has to grow like c to the n, I shouldn't have called it c, lambda to the n, or like lambda to the minus n times the power of n. So therefore, some combination, whatever the limit is, which we now know is zeta of 2, the difference will be like lambda to the minus 2n. So these are incredibly good approximations. I gave you the example of B4 over A4, which already was correct to 11 digits. Now you just compare this. This is growing like lambda to the power n, if I put n, of course. And this one already said is growing like e squared to the n, because the prime number theorem says that the least common multiples, multiple of the numbers from 1 to n, is that. And this one is lambda to the 2n. But luckily, lambda, which is roughly 11, is bigger than e squared, which is roughly 7.5, 7 point something. And therefore, the difference of this to its limit is smaller. And so there's no way it can be a rational number, because whatever that constant is, the rational number would get overtaken eventually. So that's a classical reasoning. So one knew very well, and that's the only way to prove irrationality of anything, you find very, very quick approximations. But it was absolutely crucial for that not only n was an integer, but that bn had to restrict the denominator, because if you had n factorial squared, that'd be exponential growth, and this is only polynomial, and you'd have nothing. And that's also what goes wrong for all other cases. As Pierre asked, you just can't make it. You can't make all these miracles happen. So,
just a comment about this gamma and gamma class and gamma conjecture.
Yeah. I didn't mention the gamma class, but you've just shown your knowledge. Yeah.
Actually, it's a very murky story in physics, because in physics, people usually suppose that physicists don't make mistakes, but at some point they make mistakes. It was somewhere between Moore and Minasian calculation of charges of lattice calculation formula for charges of d branes. They have thought class, and it was a mistake, or maybe not mistake, but then Mike Douglas, and then it propagated to mathematics. And then there were about 100 papers on mathematics spaces which are completely wrong, because they don't put this gamma class into the account. Yeah.
So you want me to give an example of opposite?
Yeah. No, this.
Aha, that part I didn't know. So.
Yes, so in Apéry's formula, the coefficient of one modular form in terms of tau are not only integers but positive. They're positive integers. Is there a way to see this first principles? So it's just.
I don't know. That's an interesting question. I mean, from the differential equation, if you saw anything, you would see it in T, where it's obviously positive, but you can never know what's happening in Q. But I mean, my feeling is that that's just an accident. We're in such a low weight and level that the space is one-dimensional. And so it's just an Eisenstein series. And Eisenstein series are sums of divisors, so they're sort of positive about themselves. But I have a feeling that, I could easily be wrong, but I don't see why that, I certainly don't see how to prove it, but I don't feel that there's any real meaning here.
This lambda you found from characteristic equation of this?
Yeah, that's right. So that's just standard, yeah, just from the recursion. That part's easy. So one certainly knows the way that an and bn grow, and that they have a limit, and that the difference to the limit is that. That's all without Apéry. But a priori, both an and bn would have huge denominators, huge numerators, and you would get absolutely nothing. So that's the miracle in this story is the integrality.
Coming back to the question, imagine I would start looking for this finite difference equation, but I would try playing with different prefactors taken in front of the u. It's correct to say that at the end of the day, if the limit exists, an or bn, it will be expressed only in terms of the zeta of 2, zeta of 2.
Oh, no, not at all. No, that's certainly a very good question. So I kind of brushed over that point. Remember that A, at the end of the day, as you say, when I translate it to the F side, was a modular form of some weight k. Or we could even call it k minus... Well, I can call it k, but then the degree would be k plus 1. And B, remember, was f times g tilde, where g was the modular form whose weight was 2 higher. So the g tilde is the formal weight minus k, and this is formal weight 0. So therefore, the limit, if it exists, the limit of bn over an, in general, as n goes to infinity, would be the same as the limit of the function b of t over a of t at t equals t0, which is the smallest singularity. And then the smallest singularity will always be some remarkable point from the modular point of view. That's true. In the two examples I gave in the Apéry 2, it's the point 0. I said that. But in the other case, it's not a cusp at all. It's the point I over squared of 6. It's the fixed point of the Atkin-Lehner involution. But anyway, it's some particular point. And so since B is f times g tilde and A is f, this is just g of tau 0, where tau 0 is in the upper half plane union the cusps. Okay? G tilde. Now, if G, I didn't say at all how you find the polynomial. I just defined these polynomials at the beginning. But you can do it from the L series. It's very closely related to the L series. And if G is an Eisenstein series on any group with any character and so on, then its L series is very easy. It's a product of two Dirichlet L functions. And so you can work out the properties of the L series. And so therefore, this is, first of all, known. And secondly, easy, because it's only coming from products of zeta functions or L functions. You get only L values. So in general, it wouldn't be, even then it wouldn't be values. It might be some L of n chi. And I certainly have examples where you get, say, Catalan's constant. But that's if G equals an Eisenstein series. But if you played this game at random, well, almost always you wouldn't find that it's modular at all. That's what I showed you. Here I tried to do it stupidly, just trying 100 million things, and it was only modular at all 7 times. So you would never just search at random and hope for, I mean, I did, but no sane person would. But what you do is you start with modular forms, of which we have plenty. They always have a differential equation. And then this limiting value will always be g tilde at some special point, like maybe a CM point or a cusp. But the problem is if g is transcendental, let's say it was, if you asked me what is delta tilde, if you asked me what is delta of I can tell you the answer with the Chalder-Selberg formula. But if you ask me what is delta tilde of I don't have a clue. Well, maybe I do for I because it's a symmetry point. But in general, you don't have a hope. So not at all. It's because we had Eisenstein series that were at least, and because the characters here were trivial, you got Zeta. But in general, you would get at least L series, even with Eisenstein series. So it's a trickier, a little trickier than I made it look.
Let's see. Let's speak again.
Thank you.